So before we use them to separate the angular dependence for vector fields and then gravitational fields, I think it's better if you actually try to practice with those notebooks and do stuff yourself. So this afternoon, instead of pushing forward, I'll try to slow down a little bit and let you work on the notebooks. And if you have questions, I'll go slowly and let's see what you don't understand, or if you have any questions on how the notebooks work and so on. I guess I can start, no? Okay. So there's only one color left. Okay. No, two. Oh, they're all over there. Okay. So this morning I'll do the following things. First, I'll cover the WKB approximation. So if you remember yesterday in the afternoon, we worked out one way of computing the quasi-normal modes, which is based on this continued fraction approach, where you look for a series solution of the master equation, and then you look for a certain relation that has to be satisfied by the coefficients of the three-term recurrence relation satisfied by the AN, the coefficients of the series expansion. That was the idea. So basically, instead of integrating the differential equation, what you have to do is look for numerical solutions of a complex equation in a complex variable, in the case omega. So that way gives you very precise values for the quasi-normal mode frequencies, but maybe it doesn't give you much intuition as to what they mean. So today I'll step back a little bit and I'll show you that you can obtain a very good approximation for the values of the oscillation frequencies of a black hole using the WKB approximation from quantum mechanics. Thanks, Bala. The second thing that I will do is I will apply the same techniques that I used yesterday, I think it was in the morning, to discuss conservation of energy in the scattering problem, to show that if you have a black hole that is rotating, then you can have something very interesting, which is called superradiance. Okay. So basically what can happen is that if you throw frequencies at a black hole, if you throw waves at a black hole in a specific frequency range, the amplitude of the waves can be amplified at the expense of the rotational energy of the black hole. And these can have interesting consequences in astrophysics and so on. I'll do this using as a prototype the case of scalar perturbations, because they're much easier to deal with. I can write down a simple mathematical notebook and show you how it works relatively easily. But this phenomenon happens for all bosonic fields in a rotating black hole background. So I'll show it to you in the case of scalar perturbations, and I'll state without proof that if you were to do the same for vector or gravitational perturbations, you would find the same phenomenon. And in fact, superradiance is much weaker for scalar fields, and superradiant amplification is much weaker for scalar fields than it is for vector and gravitational fields. This was computed first by, I believe, Don Page in the 70s. I'm done with the simple problems at this point, and if I want to move on and do gravitational wave physics in a black hole background, I need to deal with metric perturbations. So using spherical harmonics is not going to cut it anymore, and we need to introduce some basis of angular functions that can be used, sorry, to separate the angular dependence for vector fields, like the electromagnetic field, or the metric itself. So the last part of the lecture today, if I have enough time, is going to be dedicated to introducing vector and tensor spherical harmonics. So the general idea is that if I have a scalar field, as you have seen, for example, in quantum mechanics, you can always separate out the theta phi dependence by using the spherical harmonics, and you know their properties, and we have used them over and over again in the last couple of days. But suppose that now you have a vector field. The question is, how do you construct a set of angular functions that can be used to separate out the angular dependence of the vector field? And the simplest way, I think, to approach this problem is to take the metric on the sphere. So suppose that we work with the Schwarzschild metric. We can basically factor out the space-time, the manifold that describes the space-time, into a part where everything depends on T and R, and a part where everything depends on theta and phi. That's the way you find the Schwarzschild solution in elementary textbooks, for example. So then, what you can do is restrict attention to the metric on the sphere, and you take the spherical harmonics, and you operate on the spherical harmonics with covariant derivatives. Now, if you think of it in this way, what you can show is, number one, that the spherical harmonics are nothing but the eigenvectors of the Laplacian operator defined with respect to the metric on the sphere, with eigenvalues that are LL plus 1, basically. Okay? Second, you can take the scalar functions, which are the eigenvectors of the Laplacian, and you can operate on those scalars, the YLMs, with the covariant derivative on the sphere. So if you take those scalars and you apply a covariant derivative, you get a vector on the sphere, defined in the geometrical sense of vectors. And if you operate, instead of using a standard nabla operator, on the spherical harmonics, using the Levi-Civita symbol, then you're going to get a pseudo-vector, an object that, under parity, does not transform like the spherical harmonics anymore, but it transforms like minus the spherical harmonics under, inversion of the axis. So in this way, you can construct vector harmonics that are either polar in parity, meaning that they have the same parity as the ordinary spherical harmonics, or axial. Polar or axial is the same in this context as even and odd. So the polar or even perturbations are those for which vectors transform like the standard spherical harmonics under an inversion of the axis. And the odd or axial are the ones that transform with a minus sign with respect to the vector harmonics, the polar vector harmonics. Then you can apply another differential operator in the same way. So you can apply another covariant derivative, and in this way you get tensor harmonics. I'll show you how to do it in detail, and of course, at this stage, we're operating only on the theta phi part of the metric, because we're restricting attention to that. But then extending all of this reasoning to space-time is quite easy, because for the TR part of the metric, you can just take the TR component and stick the standard scalar harmonics, the YLMs, on top of the TR components. And for example, for vectors, in this way, you easily get a 4-vector. So I'll do it. Maybe now it sounds more complicated than it should, but when I do the math, probably it's going to be simpler. So let me remind you also that for the main goal of these lectures, we're interested in gravitational wave detection, and one of the key results that I found yesterday was the frequency and damping time of the dominant quasi-normal mode for Schwarzschild black holes, and I told you that the typical frequency that we're dealing with is something like 1.207. Kilohertz. And the damping time is something like half a millisecond for a 10 solar mass black hole. So this is a result that we found using the continued fraction technique. But when people first computed quasi-normal modes of black holes, they used a different set of tools that are taken from quantum mechanics. One thing that I forgot to tell you yesterday is this, that the technique that we use to solve the quasi-normal mode eigenvalue problem in the case of Schwarzschild, that also happens to work for the case of Kerr, is another of those things that were shamelessly stolen from quantum mechanics. In fact, the technique that Lever used to separate the, to work out the continued fraction equation for the Schwarzschild and Kerr background is taken from a paper by Baber and Assay that was written back in the 1930s that applied the same techniques to the problem of finding the electronic states of the hydrogen molecule ion. So the H2 plus, if you take the H2 molecule and you ionize it, so you only have one electron, in that case, you have a problem in quantum mechanics that happens to be mathematically completely identical to the problem that we solved yesterday. So once again, today I'm going to show you that I can steal from quantum mechanics again, and I can apply WKB techniques to the master equation that I derived yesterday to compute an approximate formula for the quasi-normal modes, which is in very good agreement with the results that I found yesterday afternoon using the continued fraction technique. And a very good agreement you can expect, because yesterday when we looked at the location of the peak of the potential, we found that the peak of the potential is very close to 3M. So, all of these ideas that I've been developing, they will all come together. So, consider the wave equation again. And let me write it like this. Okay? And let me define this quantity here, first chalk broken, as Q of R star. Okay? And also let me redefine R star to be X, because I don't want to be writing stars all over the board. Okay? So now, what you can see is that in general, if Q tends to a constant as X goes to plus minus infinity, you will have that the solutions go like e to the plus minus psi alpha x when x goes to plus minus infinity. And so if you have that your time dependence for the perturbations is e to the minus psi omega t, you will have either ingoing or outgoing waves at infinity depending on the sign of the exponential here. So the idea of the WKB approximation is that you can consider this problem defined on the real line, and you can take the function Q, We have seen yesterday that this function q has a local maximum and then it goes to 0 at plus minus infinity. Well, v goes to 0 at plus minus infinity, but now I'm considering omega squared minus v. And then you can define 3 regions here. Let me call them region 1, region 2, and region 3. And then you look for solutions of your wave equation in the 3 regions separately, and you try to match them together. Now, let's focus first on regions 1 and 3. In regions 1 and 3, what you can do is introduce an order parameter. It's called a smallness parameter epsilon, and rewrite your differential equation in this way. And then you can expand So I'm sure you have seen this before. This is the standard idea behind the WKB approximation. You say, let's suppose that we have a phase that is changing in this way, and we plug it into the differential equation, and we solve order by order in epsilon. Now, if you do this, you're going to find a differential equation that looks like this. So what you have to do is you take these ansatz for the form of psi, you compute one derivative, then you compute the second derivative, you plug everything in here, and you find the following result, that S naught prime squared So if you solve this differential equation at leading order in epsilon, you have that S naught prime squared is equal to Q. It tells you that S naught prime is equal to square root of Q, or that S naught is equal to the integral of square root of Q in dx prime up to x, let's say. Okay? Then you have to solve this equation here is called the diagonal equation, or when you work at this order in epsilon, you say that you work in the geometrical optics approximation. Then you can go to the next leading order in epsilon, and now you see that you know S naught, and you can use the equation that you read out from here at order epsilon to determine S1. So that equation is also simple to solve. You get 2 S naught prime S1 prime plus S naught double prime equals 0. And from this, you can see that S1 is equal to minus 1/4 log of Q. Okay? So this equation is called the transport equation sometimes. So when you put these pieces together, you see that in this approximation, you can write the solutions in the regions 1 and 3 has psi 1 goes like Let me make space. And psi 3, where, okay, should I define x1 and x2 as these 2 points, and let me call x0 the location of the extremum of the potential. And psi 3 goes like q to the minus 1 over 4. This comes from the minus 1/4 log q, of course. Exponential of plus minus psi integral x to x1 of q of t 1/2 in dt. So you have some approximate solutions of your differential equation to the left and to the right of the peak of the potential. Then what you want to do is find some other approximate solution at the center around the extremum of the potential and match the solution that you find in the center with the ones on the left and on the right. So the simplest way to find an approximate solution in region 2 is to say, well, I know that my function q has a local extremum there. So what I can do is perform an expansion of q around that extremum. And this gives you, of course, that q of x is equal to q naught, where by that I mean the value of q at the maximum, plus there should be a first derivative, but it's not there because I'm evaluating everything at the maximum, 1/2 q naught double prime x minus x naught squared, okay? So why is this convenient? Because if you introduce a couple of definitions that are right down here, so if you introduce these 2 definitions, you see that now the original differential equation around the maximum can be approximated by this equation here. Okay. This is just substitutions. So you take that form of q, you plug in these new definitions for the variable t as related to x, and you just define this kappa. So now if you call this guy nu plus 1 over 2, where nu is not necessarily an integer, it's just some parameter, this equation here belongs to a class of differential equations which is well studied in the literature, and they're called parabolic cylinder functions. So the parabolic cylinder functions maybe you have never seen before, but they are very close relatives of the Hermite polynomials. And this shouldn't come as a surprise. You can go to this book, which is one of my favorite things. This is a book on approximation methods in mathematical physics that is sort of the Bible in the field. And if you go and look at that book, you can find the asymptotic behavior of these parabolic cylinder functions, among other things. Why are they related to the Hermite polynomials? Well, that's pretty easy to understand, because if you remember your quantum mechanics again, Hermite polynomials pop up when you deal with the problem of the harmonic oscillator in quantum mechanics. And what we're doing here is basically taking the harmonic oscillator approximation around the maximum of the potential. So now the trick is that if you look at the asymptotic behavior of the function psi as determined by this parabolic cylinder function, which I'm not going to do, but you can look it up in that book, you see that there are certain gamma functions that pop up, and you have that the outgoing term at the horizon is going to be equal to 0 only when 1 over gamma of minus nu is equal to 0, where gamma is the gamma function. And if you remember your theory of gamma functions, this happens whenever nu is an integer. The gamma, you know what I'm talking about. The gamma function is defined as the integral of e to the minus t, whatever, okay? And those functions you can see as analytic functions of the parameter nu. The gamma function is famous for having zeros at all the negative integers. So poles at all the negative integers. And so this thing is going to be 0 whenever nu is an integer. Now, this means that I have found a condition now on Q0 and Q0 double prime to be quasi-normal mode solutions. That condition is that this ratio here has to be equal to n, where now n is an integer, plus 1/2. Now, if you remember that Q0 we defined as omega squared minus v, evaluated at the maximum, this tells you immediately that omega squared minus v, so let me write it down. I'll make some more space over here. It tells you that Q0 over square root of 2 Q0 double prime is equal to I n plus 1/2. Or that omega squared is equal to V0 minus I n plus 1 over 2 right? So you see that the real part of the frequency of the quasi-normal modes is nothing but the square root of the value of the effective potential at the maximum. And the imaginary part of the frequency is basically the curvature of the effective potential at the maximum. So the damping time is determined by how large is the curvature of the effective potential at the maximum, and the oscillation time is determined by the value of V0 at the maximum. If you now remember the form of V for a field of generic spin S, I wrote it down the other day, and this is, you have the centrifugal potential, and then you have a part that looks like this, right? Now, notice that if I take the limit where this approximation is expected to work best, that is the limit where L is large, I see that this goes to F, L, L plus 1 over R squared for any S. And so the frequencies and damping times of the quasi-normal modes in the large L limit should be the same for any value S of the spin of the perturbing field. And in fact, if you plug in this expression here, you will find that you get L square root of F C over RC, where RC denotes the location of it's 3M. It's the location of the photon ring. the unstable circular orbit, that's why the C. And you get an imaginary part which is n plus 1/2 over square root of 2. Let me erase over here. Or I can rewrite this as equal which is the result that I promised sorry, this should not have been an equal. This should have been omega equals, because I've taken a square root. So in the large L limit, this goes like L squared over R squared. So you get this for the real part. And for the imaginary part, you can just verify that this is equivalent to what I just wrote. I wrote it in this way because if you go back to the treatment of geodesics that we did on day 1, this is exactly the result that I found for the Lyapunov exponent that measures how neighboring geodesics deviate from each other. So you see that as I promised at the very beginning, the real part of the quasi-normal modes is basically L times the frequency of photons at the photon ring, and the imaginary part is proportional through this integer n to the Lyapunov exponent. And this is the leading order behavior for large L, but it happens to work surprisingly well also for low Ls. So for example, there is a notebook in the Dropbox directory where I take this expression here and I include higher order corrections. The perturbation scheme that I've introduced here can be pushed to higher orders in the WKB approximation. And Ayer and Will pushed it to third order, and more recently it was pushed up to sixth order in the WKB approximation. And the convergence to the exact results that we found yesterday is not always monotonic, but it is extremely good. And in the notebook, I actually write down, and they are also in the notes in PDF, I write down the WKB approximation at third order that you can find in the Schutz and Will and Ayer and Will papers. And you will see that all you need to do essentially is take several derivatives of the effective potential, evaluate them at the maximum, and plug them into these expressions that they derived. And you can do this for whatever effective potential you have. So once you have developed your WKB approximation for a generic potential, you can plug in whatever V you have, and you can compute quasi-normal modes for very generic classes of black hole spacetimes. Okay? So this concludes what I wanted to say about quasi-normal mode calculations. And so I'm done with this part. And the next topic that I will consider is superradiance in Kerr. So to do this, I will need to give for granted that we had derived the wave equation that describes, let's say, massless, I don't really care about the mass in this context for now, scalar perturbations in the Kerr spacetime. So I think we can, I'm not going to use this screen very much. Maybe we can lift it up so I have more space and I don't have to erase all the time. Leave it on, but just leave the screen if you can. Thanks. So, the idea is that if, once again, you consider the Klein-Gordon equation in the Kerr spacetime, and you write down your field dependence on Tr, theta, and phi in terms of some radial function r, some angular function s, and e to the I omega t, e to the I m phi minus I omega t, you get some angular equation that I'm not even going to write down. It's the equation that defines these functions that are called the spheroidal wave functions. And then you get a radial equation, and that's what I'm going to be interested in, that reads like this. This ELM is related to what I called ALM yesterday in the afternoon. It's the angular eigenvalue. You will see in the literature both E and A, and they are related by just, I think, E is A plus S, S plus 1, or something like that. They are trivially related one to the other. I will define all the quantities. So, you see that for Kerr, once again, if you write down the scalar wave equation, you get the scalar field perturbation equation, you get a wave equation, which is remarkable. But the potential looks really, really ugly. So this potential is defined in terms of the following quantities. K is r squared plus a squared omega minus am. G is equal to r delta over r squared plus a squared squared. And delta, as usual, is r squared minus 2mr plus a squared, that I can also rewrite as r minus r plus r minus r minus, where these are the two roots of the quadratic. And what else? Did I define everything? Oh, the r star coordinate. The r star coordinate is defined. For Kerr, there is more than one definition, but the one that I used here is that the r star dr is r squared plus a squared over delta. And it's not obvious, but let me write down that from this you can find r star by integration, and it's given by r star equal r plus 1 over r plus minus r minus. A squared plus r plus squared log r minus r plus minus a squared plus r minus squared log r minus r minus. I just recomputed this morning because I couldn't remember it anymore, but okay. So it's some function that looks very similar to the one we derived for Schwarzschild. In particular, it has the feature that, as you can see, when r goes to r plus, this guy goes to minus infinity, and when r goes to infinity, r star goes to plus infinity, which is what you want, right? Okay. So let me call this monster. You see that it's not just omega squared plus v anymore, okay? So let me call it v of omega and r. In fact, in general, when you separate the wave equation in Kerr, you get potentials that are complex. So they're more complicated to deal with. But so let's call this guy v of omega and r. And let's see if we can understand something about the properties of scattering in a rotating black hole by looking at the asymptotics of this potential. So what I claim is that v, I'll write it in orange because it's the key thing here, v goes like omega squared when r goes to infinity, and v goes like omega minus var pi squared as r goes to r plus, where var pi is m omega, and omega has anybody ever seen that quantity, this omega? You know what it is? No? No one? This omega here. You can't read it? Oh no. Is he the only one? Was it? Oh no. Should I use a different color, Nathan? I'll change color. I'm not going to use this anymore. Do you want me to rewrite the boundary conditions because they're the crucial thing? Can you read them? So this guy omega is called the angular frequency of the horizon, simplistically. Well, it is what it is. It's called the angular frequency of the horizon. And it's basically related to the fact that Kerr black holes are rotating and everything inside the ergo region is dragged along with the space-time. And close to the horizon, everything is dragged along at this particular frequency here. That's why it's called the angular frequency of the horizon, roughly speaking. So it's something that measures how fast the black hole spins, if you like, okay? Now, this is interesting because let me first prove this. I can prove it quite easily. So let's start by considering this, the limit as r goes to infinity. The expression looks ugly, but we can deal with it. So first of all, in the limit as r goes to infinity, you can see that delta goes like r squared, because it's r squared minus 2mr plus a squared, right? K goes like omega r squared, right? Can you read? G goes like 1 over r. Why? Because you have r, you have delta. Delta goes like r squared. Down here, you have an r squared squared. So G will go like 1 over r. dr star dr. dr star dr will go like unity because you have r squared divided by r squared. So if I take dg dr star here, G goes like 1 over r. dg dr star will go like dg dr. So it will go like 1 over r squared, right? Okay. And so if you put all these pieces together, you will see that G squared goes like 1 over r squared. so it will go to 0 in the limit as r goes to infinity. This guy will go like 1 over r squared, so I can ignore it. Here, I have k squared. K goes like omega r squared. So this guy will go like r to the 4th. And when I divide by r squared, this also goes like r to the 4th. This guy is subdominant because it's r squared over r to the 4th. So this guy I can neglect. But this guy will go like omega squared in the end, which is my statement. Okay? So this is proved. Now let's look at the other limit, the limit where I go close to the horizon. Is it clear? Was it clear? So if I consider the limit as r goes to r plus, I have that, well, obviously, delta goes to 0, right? Because delta is r minus r plus times r minus r minus. And the crucial observation is that r squared plus a squared goes to 2m r plus. Because if you look at the expression for delta, when r goes to r plus, you have delta equals 0, and r plus squared plus a squared is 2m r plus. Okay? So from this it follows that G is r delta over r squared plus a squared, so it will go to 0 because delta goes to 0, right? dg dr star so dg dr star goes like delta over r squared plus a squared dg dr. I just use the chain rule, right? So you see from this that because delta goes to 0, dg dr star will also go to 0. So you have that in the limit, let me use some color. This vanishes, this vanishes. Delta vanishes. So I'm left with k squared over r squared plus a squared squared. So I have that all of this stuff will go like, v will go like k squared over r squared plus a squared squared. But r squared plus a squared is 2m r plus. And k squared is r plus squared plus a squared, but that's 2m r plus omega minus am, right? Squared. So you see that this goes like 1, well, omega okay. I convinced you? Okay? It turns out that this is actually a very general thing. Again, I proved it for the scalar potential, but this asymptotic behavior is the same in the case of other perturbations of different spin. Now, this is interesting. This is interesting because just like in the case of non-rotating black holes, I see now that when I go very close to the horizon and very close to infinity, the behavior of my solutions is going to be a superposition of incoming and outgoing waves. But when at infinity, I still have that the characteristic frequency is omega. When I get close to the horizon, the characteristic frequency is not omega anymore. it's omega minus this var pi. So the rotation of the black hole affects the boundary conditions at the horizon in a crucial way. In particular, what you find is that I can write down the wave function in the following way. So this is going to be the general behavior of the perturbations at the horizon. And if I throw in, like I did yesterday, a wave of unit amplitude onto the black hole, I can use R or R star interchangeably because they're the same at infinity, as R goes to infinity. Right? Sorry? An exponential? Oh, sorry, here it's wrong, yes. It's just power of, okay? So if you can't see the condition up there, let me clarify. Basically what I'm saying is that because I have this, this is the limit of the wave equation close to the horizon, right? So from this it follows that R, Lm, goes like e to the plus minus psi, omega minus var pi R star. But R star goes, I wrote it here, like some real constant that I don't bother what it is, I called it alpha, times log of R minus R plus when I'm close to the horizon. So, well, alpha log will give me R minus R plus to the plus minus I alpha, okay? Is it clear? So these are the two boundary conditions. Now, what you can do is exactly the same thing we did yesterday. This is a second-order differential equation. It doesn't contain the term linear in the derivative, so the Wronskian is constant. Because the Wronskian is constant, I can consider the solution and its complex conjugate. I evaluate the Wronskian at infinity, where I know exactly what the solution is. I evaluate the Wronskian at the horizon, where I know exactly what the solution is. And I put the pieces together and I equate them to each other, because the Wronskian is constant. So when I evaluate it at infinity and at the horizon, it must be the same thing. So if you put all of this together, you find, I'm not gonna, it's really just derivatives. So at the end, you find that R squared is equal to 1 minus omega minus var pi over omega. Okay? And if typically you don't want this guy, because you only want waves that are ingoing at the horizon, you don't want waves that are outgoing at the horizon. So in the end, I can focus on the fact that R squared is equal to 1 minus so you see what's happening. Now, suppose that I have a non-rotating black hole For a non-rotating black hole, I recover the condition that r squared plus t squared modulus squared is equal to 1, because var pi goes to 0. Okay? So everything, we didn't make gross mistakes at least. But something very interesting happens when the black hole is rotating, because if the frequency omega is in the range 0 less than omega less than var pi, then the reflected wave is actually larger than unity. So if I throw in a wave packet with unit amplitude, I get a reflected wave with amplitude r, which is larger than unity. So this is kind of a miracle. And what I can do now, if I'm a gravitational Oppenheimer, I can take, so suppose that my black hole is here. I throw in my wave, and the wave as unit amplitude, it comes back with amplitude r greater than 1. And now I build a mirror. I build a mirror around my black hole. And when the wave hits the mirror, what does it do? Well, now it has amplitude r. It goes back in, gets amplified again, comes back with amplitude that is even larger, and obviously this grows exponentially, right? So this was understood initially. Yes? Well, the T out actually is, it means that you extract energy from the horizon, which is unphysical. It means that you have waves coming out of the horizon, so it only makes the effect stronger, if you like. But why would we, okay? So the key here is that this process amplifies exponentially on a time scale that can be computed. And this time scale, okay. So the idea of taking some advanced civilization that puts a mirror around the black hole is kind of a stretch, all right? Dyson wrote papers on this, on extracting energy from black holes. You can concede that one day, you know, if we run out of oil and we are particularly clever, we could use something like this to extract energy from black holes, now that we know they are there. But you do have natural mirrors out there in the universe, because what I've shown you in the case of non-rotating black holes, and what would apply here as well, is that if I consider, instead of the massless scalar wave equation, the massive scalar wave equation, then everything carries through in the same way, but the potential doesn't go to 0 anymore at infinity, it goes to mu squared. Because it goes to mu squared, you have naturally, because of the mass of the scalar field, a reflecting boundary condition at infinity. So the reflecting boundary condition is the mirror that you need. Whenever you have a mass for the scalar field, you can create superradiant instabilities in your black hole space-time that will destabilize the black hole. Whenever the frequency, which is related to the mass of the scalar field, this can be proved, is in this range. So depending on the mass of the scalar field, there are regions where you have bound states of the scalar field that are superradiant, and therefore they can be amplified and they will destabilize the black hole on a growth rate that can be computed. Now, you could have told me, you're working in the linearized approximation. So that's a problem, because whenever I have something that grows exponentially, there will be a point where my linear approximation for the amplitude of the scalar field is not going to work anymore. And the people have been working on this lately, because now we can use computers to evolve scalar fields of any amplitude you want. And the linearized approximations actually does a very, very good job at predicting how the instability grows. In fact, these instabilities typically grow on such a long time scale that it's very hard to follow them numerically on a computer. And so, you know, if you want to follow the nonlinear instability of these things, it gets pretty hard. But there are several groups, for example, Vitor's group in Lisbon and the group in Kyoto by Yoshino and Nambu that has been working on these nonlinear effects in rotating black hole spacetimes. And they find a lot of interesting effects that I will not describe now, but if you're curious, I can tell you about the references. In particular, they find that one can have something called a Bose-nova, which is a collapse of the scalar field that can produce large amounts of scalar radiation. Even those large amounts of scalar radiation are not large enough to be detectable unless the Bose-nova happens really close to us. But it's very interesting that at least conceptually they can happen. Okay? So, again, for now, this is all I wanted to say about superradiance. How much time do I have left? 30 minutes, okay. So, yeah, 30 minutes, okay. So the splitting of the lecture this morning is working pretty well. So first 30 minutes I did this, second 30 minutes I did this. Now I'll try to give you an introduction to how do we go beyond the scalar field model. Some years ago, people would have come to me and said, why do you study scalar? Yes?
So it extracts the rotational energy.
Yes, yes, yes.
So then why does it become unstable at the peak?
So, in fact, the end state of the superradiant instability is not understood. It is very likely, as you say, that in the end, you have a non-rotating black hole and a large scalar field outside. But because we cannot follow the nonlinear evolution over the time scales over which the instability operates, this is not settled yet. But yeah, very good question. Yes, but it does grow exponentially. What you can do, in fact, is very interesting. Okay, maybe I should say this. What you can do is you can make plots in what Arvanitaki and others call the black hole Regge plane. So suppose that I have the mass of the black hole on the x-axis and the spin of the black hole on the y-axis. I told you that the strength of the superradiant instability is maximum when mu m is of order unity, where mu is the mass of the scalar field and m is the mass of the black hole. And I gave you arguments some days ago why this means that for, say, a black hole of 10 to the 9 solar masses, I will have a mass of the scalar field of about 10 to the minus 18, and if I take a solar mass black hole, it will be 10 to the minus 8. So suppose that I am in, there are scalar fields in nature, for example, axions, that have the right mass such that the instability is active. Then what you can show is that comparing the instability growth time scale with, say, the typical time scale for black holes to accrete matter, so that they will spin up again. This is the simplest thing you can do to determine what is going to win, accretion or the spin down. Accretion will typically spin your black hole up. So what is going to win? Accretion that spins the black hole up, or superradiant instability that tends to spin it down. So you can equate these two time scales. The time scale for superradiant instability you can compute in perturbation theory. If you equate these two things, you find a window like this. For any given mass mu of the scalar field. So you can say that all the values of the spin that are above this window would be excluded. And then you can go out and get your favorite review on measurements of spins for supermassive black holes or, say, stellar. And if there are measurements in that window, you can exclude a range of values of the mass of the field. Because say that you have a point here that tells you I have measured a black hole spin and mass that correspond to this with a certain error bar, then you can exclude all the masses in the range from here to here that would be incompatible with a measurement of that spin. So any spin measurement rules out a range of scalar field masses. For scalar fields, okay, this is interesting, but you know, whatever. The thing is that, as I said at the beginning, for vector fields and gravitational fields, the instability is even stronger. So you can rule out the mass of hypothetical massive photons to a very constraining degree. The problem here is that we wrote a paper on this, and then people came to us and said, well, but you know, you are ignoring plasma effects. If these are real photons, then the physics is more complicated. Okay, but there are dark matter models where you have hidden photons that interact very weakly with matter. And so for hidden photons, certainly you can rule out their masses to a very high degree by this argument. Gravitational fields, the instability gets even stronger. So if you work in a simple model where you use, well, okay, I'm going too far here, but you can consider linearized equation for massive gravity. We don't have a theory of massive gravity, but we have a linearized theory of massive gravity, more or less. And so you can take the linearized equation in a curved background, you can compute the instability timescale, and you can rule out masses of the graviton below, I believe, 10 to the minus 25 or so, which is very close to cosmological values, which would be of order 10 to the minus 33, when you assume that the mass of the graviton is of order the Hubble scale. So, you know, you get very close to saying, well, okay. It's the mass of the black hole. So this is some mu1 and mu2 for the scalar field. For each mass of the scalar field, you have a different exclusion window. This, in the literature on this stuff, they're called holes in the Regge plane. Okay. Yes. If it goes to the non-spinning case, yes, the angular momentum is equal to 0. So what's the question?
So the total angular momentum must be from the, where does it go? Where does it go?
Well, the energy in the angular momentum has gone into the scalar field. Yes. Yes. You're extracting the rotational energy of the black hole. So if you think of it in the, you know, the papers by Christodoulou and company on the irreducible mass of the black hole. How much mass can you extract from a rotating black hole? If you look at those papers, the maximum mass you can extract is something of order 30%. And so in this case, you can expect that you can extract at most about 30% of the total mass energy of the black hole by spinning it down.
Yeah, and that goes to the scalar.
Yes. I didn't understand the question. The Penrose process. Okay, very good question again. So who heard of the Penrose process? Very good, okay. So the Penrose process is basically the particle analog of this. The particle analog of this, because in the Penrose process, what you have is this. You have a black hole, you have the ergo region. The ergo region is characterized, if you remember what I wrote down on the blackboard the other day, it's characterized by GTT changing sign, roughly speaking. So what this means is that inside the ergo region, you can have particles with negative energy. So Penrose's idea was, suppose that I throw in a particle, say a photon or whatever, from infinity into the ergo region. Then, in the ergo region, this particle breaks down into two particles, one of negative energy and one of positive energy. The particle of negative energy falls into the black hole. Okay? So the particle that comes out by conservation of energy has energy larger than the particle that fell in initially. So you have extracted rotational energy from the black hole, and the particle that comes out has more energy than the particle that came in. So this is completely equivalent to the wave scattering process that I'm considering here. The waves that have are in this frequency range are equivalent to particles that fall in the ergosphere and break down in the original Penrose process way. and you are extracting energy whenever you are in the superradiant regime. All of this was understood by Zeldovich back in the 70s, and there's a revival now of these ideas because of the interest in dark matter, and several people are thinking hard about this. Recently, there was a paper by Schnittmann, for example, that showed that this is the simple variant of the Penrose process, but you can consider a different variant of the Penrose process where you have two particles going in and two particles. So this is more realistic than a single particle breaking down, because you can imagine that you have some accretion disk and the particles go in and they collide, and then you have a 2-2 process. So the question is, what is the maximum energy that you can extract? And the old calculations in the 70s, it turns out they were wrong, because they ignored the fact that when you throw a particle in, that particle can bounce around the effective potential of the black hole. So when you have the collision, one of the two initial particles is already going out, and so the likelihood of producing a high energy particle that goes out as a result of the collision of Penrose process is much higher. We wrote a PRL about this, but don't, okay, we can talk about it in the coffee break. I need the other 30 minutes, or 20 now, okay? Okay. So, superradiance. Now, I told you that I want to go a little bit. Typically, people, when they do an introductory course on black hole perturbation theory, stop here, because if you want to do vector and gravitational perturbations, the math gets pretty nasty. But, they told me we have 15 postdocs, 15 grad students, they're all very good, so I'm like, okay, I'll push them. So be ready. Now, this is actually where it gets interesting to me, because what I can do is I can consider, instead of scalar fields, which are easy, electromagnetic fields, for example, or gravitational fields. And I want to do the same in detail and derive the master equation that I promised I would find. But I need to develop a little bit of mathematics. So when I was an undergraduate student in Rome, what I had to do is open up the Zerilli paper from 1970, get scared, get very scared, find out that half of the paper was wrong, redo all the calculations, and, suffer. But in particular, this paper by Zerilli has enormously long appendices that list the so-called Zerilli-Matthews harmonics. And fortunately, Valeria Ferrari at the time wrote a very nice set of lecture notes explaining more or less how these tensor harmonics come about. But the notation was not let's say, pedagogically, I don't think that would be the best way to do it. So I'm going to do it in a way that I think is much simpler. And I have to thank the fact that after my undergraduate thesis, there was a series of papers by Gundlach and Martin Garcia that popularized an old paper that was written by Gerlach and Sengupta in 1978 that everybody ignored for years and years, where these tensor harmonics are introduced in a very simple way. So let me explain the idea. The idea, like I said at the beginning, is if I want to expand a scalar, I have a scalar function, phi of t r theta phi. I want to expand my scalar field in a spherically symmetric background. What do? I say, well, I take the spherical harmonics, and I expand my field in spherical harmonics, and I've done the calculation on the blackboard. And you can get your radial wave equation. Good, it's all good. Now, if I want to do the same for a vector field, what am I going to do? And the idea is this. Let's take my coordinates on the manifold, x mu, and let's write them down as where ya corresponds to TR. And ZA corresponds to theta phi. Okay? So now, consider the metric on the sphere. The metric on the sphere, of course, is ds squared equals gamma AB dz A dzb. Sorry for this screeching. Maybe I should change chalk. And this is nothing but d theta squared plus sine squared theta d phi squared, right? So I can introduce, as usual, the determinant of the metric on the sphere. That's going to be square root of gamma, which is nothing but sine theta, right? And I can introduce the covariant derivative on the sphere. Okay, you just go to, if you want to do these calculations in practice, you take the header of one of the Mathematica notebooks that I gave you. Instead of working in 4 dimensions, you work in 2 dimensions. You write this metric instead of, say, the Schwarzschild metric, and then you can do differential geometry in 2 dimensions, right? So we know how to do it. Also, I want to introduce the Levi-Civita symbol. So suppose that I work in Cartesian coordinates, and I'm in 2 dimensions. If you remember, the Levi-Civita symbol is usually defined in 3 dimensions, because that's where we're interested in it, and in Cartesian coordinates. And let me remind you, in 3 dimensions, you define it as epsilon ijk equal to 1 if ijk is an even permutation of 1, 2, 3. And minus 1 if it's an odd permutation of 1, 2, 3. Remember? In 2 dimensions, you can do the same thing. So you can define a Levi-Civita tensor in Cartesian coordinates in 2 dimensions. And if you write it down as a matrix, I think you can easily convince yourself that it's going to be given by 0, 1, minus 1, 0. Because the Levi-Civita symbol has to be 0 when I is equal to j, 1 when ij is 1, 2, and minus 1 when ij is 2, 1. But this is not a tensor. This is a tensor density in the language that you can find, for example, in Poisson wheel. If you want to turn this into a tensor on the sphere, you have to multiply by the Jacobian. So you make a coordinate transformation from Cartesian coordinates to spherical coordinates, and you get epsilon AB, which is what we need, which will be given by gamma times epsilon A bar B bar, if you like. So it will be given by 0 sine theta minus sine theta 0. Good. So now I have introduced a Levi-Civita symbol in 2 dimensions on the sphere. Okay. Now, the key results are, I cannot use other colors, but okay. What about blue? Does blue work? So first of all, I can show that
There is a kind of whitish background after you wrap it up. Yellow or red?
I don't have yellow. Satya used it all. He likes it. He used all the yellow. So what should I do? Should I write in white?
Yeah.
Okay. Clear? So this is telling you that box Y is minus lambda Y on the sphere, where box is the covariant box operator, okay? Which is a much more elegant way of writing down the Legendre equation that we used over and over again. It's much more elegant also because if you are working with black holes in d dimensions, you can easily generalize this result to d dimensions. You can show that if you have an n sphere, all that changes is the value of the eigenvalue there. I forget now, but it's something like L plus n minus 1, where n is the number of dimensions, okay? So if you want to do d-dimensional black holes, you can use this formalism right away. So for example, I will do the problem of a particle falling into a black hole. Some years ago, well, 10 years ago, we did the problem of a particle falling into a d-dimensional black hole, and you can take the same mathematics and do the problem in the same way. So now, one key property of the spherical harmonics that I want to remind you is that if I take a parity transformation, parity means that I send theta phi to pi minus theta, phi plus pi. This is an inversion of the axis, right? So theta is over here, minus theta is down here. Then minus phi, I send it to the other side. So this is an inversion of the axis, right? Under a parity transformation, you have that y lm of pi minus theta phi plus pi is equal to minus 1 to the L y lm theta phi. Okay? So whenever the spherical harmonics or their derived quantities transform like minus 1 to the L under an inversion of the axis, I will call a given quantity even or polar. If under an inversion of the axis a quantity transforms like minus 1 to the L plus 1, then I will say that it is odd or axial under inversion of the axis, okay? For example, a vector is even. A pseudo-vector like the angular momentum is odd in 3 dimensions, okay? So now I have my spherical harmonics, and I want to construct vector harmonics on the sphere to expand, say, an electromagnetic A mu tensor, A mu vector. So how do I do this? Well, I introduce polar vector harmonics in this way. I take nabla A y L m. So YLM is a scalar quantity. I apply a vector to a scalar quantity. I get a vector. A vector on the sphere is a 2-dimensional object. So you can compute it. And in fact, you can tell me the result. What am I going to get? What is the theta component of this vector? Anybody? I'm taking the covariant derivative with respect to theta and phi of YLM, which is a scalar. So what is the covariant derivative of a scalar? It's the ordinary derivative. So what is the theta component of this vector? Y comma theta, okay? So I'll call this a polar vector harmonic. Similarly, I can construct an axial vector harmonic by taking S, A, Lm, and I'll call this Y, A, Lm. YA, the index, A reminds me that it's a vector. The capital A reminds me that it's defined on the sphere. It is two-dimensional. LM because, it's a decomposition. So then I can define an axial vector harmonic. And how do I define it? I take epsilon AC, gamma BC, nabla B, Y, L, M. Does it make sense? Because gamma BC nabla B is nabla C upstairs, and then I'm multiplying by the Levi-Civita tensor. Think of the definition of the angular momentum in Cartesian coordinates. It's epsilon ijk, nabla j, xk, right? So this is the two-dimensional generalization of the definition of the angular momentum in epsilon ijk, xj, nabla k, I should have said. But you understood what I, okay? So this is the two-dimensional definition of the angular momentum, if you like. It's axial, because it's a Levi-Civita times a vector. So this guy you can compute, and I will ask you to do it this afternoon. Take the metric, plug it into Mathematica. It's easy. This you can even do by hand, okay? Because the Christoffel symbols for in 2 dimensions, there's like very few of them. So you can do it by hand, but and this is what you find. Okay? Then I can introduce polar tensor harmonics. In this way. I introduce something that I call ZAB-LM. So the idea here is that you have two possibilities of constructing a polar tensor out of the polar vectors that we defined, out of the quantities that we defined. One is you just take the metric and you multiply it by a spherical harmonic. The other is you take two covariant derivatives of the spherical harmonics and you get a tensor, okay? This is just a particular combination that is used very often in the literature, but I could use either gamma or nabla A, nabla B, or ZAB. There are 3 of them, but only 2 are independent, okay? And I can construct axial tensor harmonics. So what would you do if you want to construct an axial tensor harmonic? So you need to take a tensor, an axial vector harmonic, and then what do you do to it? Or you apply a covariant derivative to an axial vector, right? You need one Levi-Civita and you apply a nabla to, so you will get, you also need to symmetrize, so you can construct this. SALM equal 1/2 nabla B SALM plus nabla A SBLM. Okay? Now, if you compute these guys, you'll see that they are given by 1/2. I'll define everything. Okay, where XLM is 2 and WLM is YLM, comma, theta, theta. So these two combinations, X and Y, X and W, sorry, they appear all the time in black hole perturbation theory. And now you know why. So basically, you take the sphere, you construct the spherical harmonics. From the spherical harmonics, you construct the vector harmonics. They can be polar or axial. Then you take another covariant derivative, and you construct the polar and axial tensor harmonics. And this is what you need, okay? I'm over time, so I'll stop here. The next thing you need to do is, I only worked on the sphere for now. I need to stitch on the TR coordinates. For a vector, what I would do is I would take these guys, and then I would add a component Y in the T slot and another component Y in the R slot. That's for the polar. For the axial, I don't need to do anything because I just put at 0. So I will have polar and axial 4 vectors that I can then use to expand A mu and find my electromagnetic perturbation equations, the Maxwell equations on the black hole background. So that's going to be a little more complicated, but not too much. And I can easily do it this afternoon. Tensors.